Very good. Okay, all right. Thank you, Susan. Yeah, welcome everybody to the session. My name is Andy Goetz. I'm a research scientist at San Diego Supercomputer Center. I'm a computational chemist by training, and we have computationally intensive codes that we've been porting to GPUs in order to take advantage of GPU performance and computational power. And so I'm going to talk a little bit about that, trying to give you a brief overview here, looking at the topics that we're going to cover, starting with a little bit about hardware overview, background, just a few accelerated software examples based on the codes that I've been developing. And then I will go into programming GPUs, focusing on NVIDIA GPUs. Those are the GPUs that we have here in Expanse at the San Diego Supercomputer Center. I'll talk about GPU-enabled libraries and give you a brief introduction to Qt programming basics. In these slides, I have much more material than I'm going to be able to go through with you, but I decided to leave this in so you have this as a reference. And we'll skip over that and you'll see that. So there are also some code examples that I have for some of those sections that we're just going to gloss over. And after this, we'll have a break. So let me think about this. It's 10. If we make a halftime break, that would be about, let's see, so until 1:30, then 11:15 or something like that. No, wait, it's 10:45, around noon or so. We should try to get a little bit of a break. Let's see how far we get until then. And then we'll access GPU nodes. So the slides and as well the source code we're going to use and look at and information on how to log in and so on is in the GitHub repository. So if you will pull that up, I'll show that later to you. But there is in the README, there's instructions that you can literally go through and that you can follow to do some hands-on exercises on Expanse with Qt code, compile it yourself and run it. And then we'll talk about OpenACC and do some hands-on exercises again with OpenACC. And hopefully I can fit this all in until 1:30 p.m. All right, so with that said, let's start with a GPU hardware overview. And I like to start with the very basics. You know, a GPU basically, if you ask what is it? It's an accelerator, it's a specialized hardware component to speed up some aspect of a computing workload. And not unlike some other coprocessors that you would find in older PCs or also modern hardware. For instance, you know, to speed up floating point operations, or nowadays you have FPGAs, or you have dedicated processors, you know, for all sorts of operations. In the last few years, in particular, for machine learning applications. So this was really developed for computer graphics, which is been driven by a huge gaming industry. So a lot of money went into development of this hardware. That's why it's so powerful today. Originally had only fixed function pipelines, and then about like 15 years ago or so, frameworks were developed and the hardware was changed in such a way that you can actually program these beasts with a general purpose programming languages with some extensions. That's basically Qt for C, C++. And now there are other ways as well. So really accessible for general purpose computations with some limitations because of the simplified core design that they have in comparison to a CPU. So, branch caches, not as big and so on, partially exposed memory hierarchy, and of course the parallelism that you really have to take into account. Now the question is, why is there a big interest in GPUs? So if you look at, all the big supercomputers, basically everybody has nodes with GPUs in them. The big exascale computers by DOE, the biggest machines, they all are get the majority of the raw compute power from GPUs. Used to be all NVIDIA, and now there's NVIDIA, there's AMD. At Argonne, there's going to be a machine that's going to have Intel GPUs actually, so Intel is also getting into the game. And if we look at Moore's law, if you're familiar with that, it's basically the transistor count in integrated circuits doubles about every 2 years. So that's an exponential growth, right? And that still holds. So if you look at that plot here, it's not completely up to date, but what you see on here still holds effectively. So the number of transistors is still growing exponentially. However, if you look at what happened about here in the mid 2000s, is several things. First of all, the clock frequency wasn't increased anymore. So if you're a little bit older, like myself, you remember megahertz, 100 megahertz processors, and then at some point gigahertz processors, and that's where we are stuck. So you can't really up the clock frequency. The single thread performance is slightly increasing because there's still innovations happening, but it's basically leveling off as well. That means serial code just doesn't run fast anymore just because you wait for a new generation of a processor, at least not much. So what instead happened is, it was that we went into this multi-core regime. So now we have all these multi-core processors. And if you look at SDSC Expanse, we have 2 AMD CPUs in there. Each CPU has 64 cores, so total 128 cores on a single compute node, right? And so the number of logical core increases. And so what you have to do is you must write parallel code. And GPUs take this in some sense to an extreme because you have thousands of processing units, compute cores equivalents effectively on each GPU, and you need to be able to program that. If you're able to do that, now what you see here on the left and on the right is the peak floating point performance of GPUs. Those are older GPUs, so I've taken this from this website here that's not been updated recently, but those trends are still valid as well. And the left is single precision, so 32-bit floating point numbers, and here double precision, 64-bit floating point numbers. And what you can see is, of course, the floating point performance has been increasing for CPUs, but GPUs have orders of magnitude larger floating point performance. So if you do number crunching, you can do it, and you can parallelize it efficiently. You can do that quite effectively on modern GPUs. So you get a lot of compute power here, right? So we are here in the tens of teraflops regime. One thing to keep in mind is, on the left, you see these are all like consumer gaming type GPUs. And you won't see them on here because they typically are handicapped in some sense. The chips are manufactured in such a way that they can't do the same, even if it's the same type of processor, the same generation and architecture, they will not have the same double precision, so FP64 floating point performance. So if that's important for your codes, it's important to get this data center GPUs. So these are the really expensive data center GPUs of the type that we have at SDSC. So this is a Tesla P100. This is an accelerator that was in Comet, the predecessor of Expanse, and Expanse basically somewhere up here is, the Volta architectures. Another thing that's very important is look at the left graph here, is the memory bandwidth. So many codes nowadays, because we have such a high floating point performance, the memory bandwidth has not been keeping up with. So meaning how much data you can move in a given amount of time from memory, from the RAM to the processor and back, right? And that is very important because if you don't have the data on the processor to do the computations, the processor is just sitting there idle, not doing anything. And many algorithms and problems are memory bandwidth limited. So you actually don't use the full floating point performance. It's hard to get the full floating point performance out of a GPU unless you have a problem that really is ideally amenable, like dense linear algebra. Typically, you can get very high peak floating, close to the peak floating point performance. In any case, what you see is that GPUs have a very high, due to the memory they're employing and the memory bus and so on, the architectures, they have a much higher floating memory bandwidth than CPUs. And so that's a significant advantage as well. And then you need to look at the power consumption. Modern GPUs can draw a significant amount of power. So some of the GPUs, are up at 300. I think the V100s in Expanse, they can draw up to 350 watt, and CPU typically draws around 150 watt or 200. So it depends. So you consume more power, so you need to take that into account to be fair, to have a comparison about running costs, operation costs, right? And so here's a summary. That was from 2018. That's basically state of the art when Comet was about to be installed. So these were state of the art, Expanse, state of the art CPUs back then from Intel. They have a lower core count than AMD equivalents. But in any case, 56 cores per node, and here you'd have, the Tesla V100 accelerators. So GPU that sticks into a PCI Express bus on the server, and a comparison of the peak floating point performance that you can get. So these numbers are approximate because it's hard to really measure what consists, peak floating point performance. Depends on the operations that you do and so on. But you can see that you get much more out of the GPUs for the same amount of dollars that you spend, and for a comparable sort of like power consumption, a little bit more, right? So to be fair, there's one more, and the memory bandwidth, of course, is very, very, very high. This is half precision, so GPUs actually support also, different types of precision models that have been developed in particular for deep learning applications. So that's important, that often you don't have that on CPUs. And you see the memory bandwidth, so it's much higher on the GPUs, right? Almost a factor of 10 in this case. There's another thing though, of course, because these guys are actually sitting on a PCI Express bus, and we'll get back to that. When you have data, you load it into memory, and that memory is the memory that's attached to the CPU. And then you have to send it to the GPU to do some processing on the GPU. So if you have to move a lot of data forth and back to the GPU, that's a bottleneck because the PCI Express bus is just much slower, right? And then the question is, you write code, you want that the code still works next year on maybe a different vendor and so on. And the question is the code portable? And I would say that nowadays also GPU code is portable. CUDA is really specific for NVIDIA GPUs, but you have other, these are, so OpenCL, first of all, works on any type of architectures, also for, CPUs, ARM-based systems, and so on. And then Pragma-based methods like OpenACC and OpenMP, they can be used to upload work to GPUs. We'll look at OpenACC later. CUDA is, in some sense, was not portable, but nowadays there are code translators that you can use to translate the code to different frameworks, because CUDA runs only on NVIDIA GPUs. Then, right, so if we're talking about the performance, and just to put this a little bit in perspective, I like to do this. This is now already over 20 years ago, but that was the ASCII-Byte supercomputer at Lawrence Livermore Lab that had a peak floating point performance of 12 teraflop. That was the #1, the fastest supercomputer in the world back then. It cost $110 million US. It filled an entire data center. And if you compare this to Expanse, so we have the CPU nodes, and we have an aggregate. So let me think. I don't want to get this wrong. So each node gets already 4.6 teraflops floating point performance. But then adding the GPUs, we don't have that many GPU nodes. I think there's another rack now that's available that has been installed a short while ago. So these numbers might not be exact about the total compute power. But so from those GPUs alone, we also get us 1.6 petaflops, right? So that's 3 orders of magnitude faster, right? So that's super powerful if you think about it. And the whole hardware cost here was just about $10 million US, right? And that was 2001, right? So 110 million US dollars nowadays would be much less back then. So much cheaper, much more compute power, obviously. And you can build your own box that's basically a supercomputer compared to what we had 20 years ago. So these are the NVIDIA gaming GPUs, and the double precision performance, like I told you, is not that great, but still, it's 10% of the entire machine here. But if you can get away with a single precision, it's, you know, you have 4 GPUs, you spend about $4,000, maybe a little bit more for all the, you know, motherboard and so on. But let's say you have, you know, $5,000-6,000, you can build a machine that has 10 times the compute power of the fastest computer in the world and 20 years ago. So all you scientists, researchers, you have a lot of compute power at your fingertips, and so do something great with it. So we have all this compute power, right? So your manager comes to and says, well, our servers are using too much electricity. We need to use GPUs because, you know, then we need less GPUs, they're more powerful. And he says, I did my part by reading about GPUs in a trade journal. Now, and a while later, he comes, hey, part taking so long. So we need to port our codes, and that's not always trivial. Sometimes you get very, very quickly, very easy. You can speed up your codes very quickly with OpenACC or just with Python, dropping in libraries and so on. But, you know, if you have to rewrite your code using CUDA, that can be a significant effort. And one thing you have to keep in mind if you think about the real estate that you have on the chip, so the silicon that is available, you know, on a CPU, you have a lot of like, you know, control hardware and caches for, you know, prefetching, branch prediction, and all sorts of stuff. And then you have a few of the processing units, arithmetical logical units, right? Comparatively, on a GPU, you have thousands of simplistic compute cores, right? And you have much less cache and control units. So the GPU compute cores, they operate in lockstep. So you have to write code in such a way that, you know, you can do the same operation like on a vector processor and a vector units, right? Vector processing units. You do vectorized loads and stores, and you need to think about these things, and you need partially to manage the memory hierarchy. So this has been gotten better. You don't have to think about everything, but you still, even some of the directive-based programming approaches, if you don't know how the underlying architecture works, you know, it's not automatic that your code will run very, very efficiently on the GPU. So it takes some work. Then if we look at the GPU architecture, this is an old NVIDIA slide from 2008, right? I mean, this was an architecture that actually was sold then in 2008, 2009. This was I believe the first data center GPU server that was sold, right? And I'm showing this because the basics of how our GPU processor looks like and what you have to keep in your mind didn't really change. So back then, basically what we have is we have several of these so-called multiprocessors. So you see them here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this schematic here. Each of those multiprocessors, so think of those as different CPUs if you want. So anyway, that you have like different sockets, right? Sort of. And each of those has multiple compute cores, like single precision and double precision compute units, special function units, and so on. So, and its own, you know, cache and shared memory. So the cache on this processor doesn't know anything about the cache in this processor, right? So these are independent. But all these processes in here, they operate in lockstep. So you have to parallelize the code to utilize all those compute cores and all those different multiprocessors. And you have to write the code in such a way that it does the same operation in all of those compute cores at the same time, right? Yeah, so the other thing to keep in mind is that there is this multi-threading instruction issuer that handles many more threads than processing cores. And so when you launch CUDA kernels, so-called kernels, those are the compute units, the functions that do computation on the GPU. You want to launch them with many more threads than you have actually compute cores available. And, you know, CUDA handles that, you know, the GPU architecture handles that automatically to schedule them at the right point in time. And that helps mitigate memory bandwidth issues because, you know, while data is being requested, you know, some other threads that you have launched may have the data already and they can do some compute while the other threads are waiting. And that hasn't changed. So this is all still the same. There's many more features now that the GPUs have. So we have tensor cores, for instance, and they accelerate so-called like matrix multiplication and accumulation operations. And they can do this for FP64. So different data types, like here, this tensor float 32, B float 15, and FP16. So that's specialized hardware that basically does this sort of operation, right? So you can do something like also mixed precisions, right? Where you have, say, 16-bit floats, where you do a matrix multiplication and you add that into either 16-bit or 32-bit float for accumulation results output. So that's schematically represented here, right? So you have the input of you do the matrix multiplication and add that onto your corresponding output matrix. And those are basically tensor operations that are used in deep learning neural networks, right? So that's why they've been implemented specifically in hardware. And it runs extremely fast. So if you have these sorts of like machine learning, deep learning applications, so you have like these fully connected linear and dense layers, convolutional layers, and recurrent layers. They all benefit from these tensor cores. And you can use those also for mixed precision matrix operations. So there's a QBLAS library that supports that. Then the hardware characteristics change across GPU models and generations, but in some sense, it's not different than using different GPUs, CPUs, right? So you write code that should run independently on which generation of GPU you use. I mean, it's not entirely true. Instruction set architectures change, but for if you recompile the code, it should run. And what changes typically the ratio of the floating point performance FP32 to FP64. Memory bandwidth, number of compute cores and multiprocessors, the number of threads that the hardware can execute, the number of registers and cache size you have. So you might have to optimize kernels for that. That's not different than optimizing code, for cache optimization for CPUs, for instance. And of course, the available GPU memory that you have. So if you look here, those are different generations. So the P100 was in Comet. V100, that's the Volta architecture that we have in Expanse, and that's the Ampere architecture. And there's actually new architecture now after that's been coming out. That's the Hopper architecture. I don't have data for this on here, but you see the single precision cores per multiprocessor didn't change. You still have 64. So there's 64 cores on each multiprocessor, and the P100 has 56 multiprocessors. The V180, the A100 has 108. So you see, you have like, it's been increasing, but so in the order of like 5,000, 6,000 cores, and correspondingly, the floating point performance has increased. So we have, about 7 teraflops of FP64 floating point performance on the V100s, each V100. The warp size, that's the number of cores that actually, instructions that issue in lockstep. So that's 32, that didn't change, but it's not guaranteed to stay the same. It's just something to keep in mind. So you shouldn't write code in such a way that this is an assumption that it is exactly 32. Then, I already mentioned that you have to explicitly manage the memory hierarchy. So think about the CPU memory, the GPU memory, and then you have shared memory on the GPU, texture memory, constant memory. There's something that's called unified memory, where you don't have to think about, CPU and GPU memory. And CUDA will handle it automatically for you, but the memory hierarchy still exists. So this helps you to prototype code quickly. But usually people will handle that explicitly once they get to performance tuning. And then NVIDIA and AMD work a little bit differently, although, basically, if you look at it, a lot of the nomenclature is the same. And they work very similar with GPUs. There's something called compute capability that you can look at, and that basically is based on the hardware version. So from Pascal to Volta, Ampere, then there was Turing, and then there's the Hopper architecture now. And depending on the, there's different types of GPUs always, like gaming GPUs, workstation CPUs, and then the data center GPUs, which are cheap to very expensive, and features that being switched off the more you go to the cheaper hardware. But if you check what compute capability you have, you will see what features of CUDA are supported. It's not something that you typically have to take care of, but something to keep in mind. Overall, these changes from architecture to architecture, what that means for your program, really, there's two things that you have to keep in mind. Threads. So you should never write code that has an assumption for how many threads it will use. It's a little bit, like an MPI code or OpenMP code. When at runtime, at launch time, you'll determine the type of hardware that you have, how many cores do they have, and then you launch. So you use CUDA calls in this case. You can query the hardware configuration of the GPU, and then you launch a certain number of threads, and that typically needs to be many more than the processing cores to help avoid or hide memory latency, memory access latency. And data types, in particular, if you want to use the cheap gaming GPUs, you have to avoid using double precision. And then you can get very high performance. I'll show you an example about that. But you have to keep in mind that, of course, if you need that precision to maintain numerical accuracy, then there's no way around that. So you need to be careful with this. Then you've heard already a lot about expanse. I'll just go briefly over that again. So we have these scalable compute units, and then each of these scalable compute units has 4 times 4 GPU nodes, and so each GPU node has so we have a total of 208 V100 GPUs. So we have 52 4-way GPU nodes. So there's 52 nodes. Each node has 4 GPUs. Yeah. So later you'll get access to one of those GPU nodes, and with 1 GPU assigned to you. Now, if you look at this, so this is not a picture from Expanse. I just grabbed this from somewhere, but effectively, it sort of looks like that. So in Expanse, we have this GPU sitting on the PCI Express bus, the V100s. But here you'd see a server that has basically 4 GPUs. That's how the GPU looks like. So you have the processor. Here you see the memory banks. That's the RAM of the GPU. If you can buy those GPUs that go into a PCI Express slot, they look like a gaming GPU that you would buy for it's basically a brick, and you stick it into the PCI Express slots, like if you were to build a desktop workstation. Here are the CPUs, processor to processors, and you have the memory for the CPUs. And yeah, the GPUs, they just have the memory right on them. Like just you buy the GPU, you can't add or remove memory. So in our case, the GPU nodes, they don't have AMD processors. We have Intel processors. There are 2 20-core Intel processors. There's 384 gigabytes of RAM. So that's the CPU memory. And then there are 4 NVIDIA V100 SXM2 GPUs, and each of those GPUs has its own memory, and there's 32 gigabytes of this so-called HBM2 memory that has, quite high memory bandwidth. So speaking about how quickly can you get the data that's stored in here to the processor and back. And then we have also, scratch disks on each node, 1.6 terabyte NVMe per node. So there are other things that if you were to, if you want to use multiple GPUs, or you write code that basically runs across multiple GPUs and communicates between the GPUs, then there are other things. We have higher speed interconnects between the GPUs, but you have to be careful. So there's the CPU 0 and CPU 1, and there's like two GPUs that are effectively closer to CPU 0 than to CPU 1, and the memory bandwidth on the PCI switches, of course, slower than the communication that you can have between the GPUs. There's some information here in that user guide. If you want to know more, please take a look there and/or ask questions. So this is an information. So NVIDIA SMI is the NVIDIA System Management Interface. Can give you information about the GPUs. You'll try this as well. It has an option topo, and so if you type topo -m, it's going to tell you basically how the GPUs are interconnected, right? So I mentioned briefly this, faster interconnects, these NV links. So you see they are running at 50 GB per second, as opposed to PCI Express bus, which is slower. So if you wanted to send data from GPU 1 to GPU 2, in a traditional system, you'd go through the PCI switch. You don't have to do that. So you can see actually that, GPU 0 and GPU 1, they're interconnected by this NV2 interconnect. So they can talk faster to each other than in a system where you have to go through a PCI Express bus. So that's special hardware. And the CPU affinity is basically, which CPU they are connected to on the PCI Express switch, right? And some information here basically about if you send data between GPUs, how it would travel, right? And this is the network interconnect that's sitting on the PCI Express bus. So that what you have to use if you need to communicate between GPUs between different compute nodes. Yeah, I talked about this. This is how the GPU looks like. This is a diagram you've seen before, the one from the Tesla, the early Tesla, the first this C1060 card. It looks the same, only now it's different. So you have all these multi-processors. Each of those has 64 cores, and you have many of them, right? And then you have an L2 cache actually that is accessible by all of the multiprocessors. Each multiprocessor has its own shared and cache L1 cache memory. And shared memory is basically user-managed cache memory. You have the memory controllers, and then this is the memory that you see sitting here on the side. This HBM2 memory, which is very fast memory. And then you also have the high-speed hub with these NVLink interconnects when you want to send data to another GPU, communicate with another GPU. Right, so 32 GB of RAM, 80 SMs, 64 FP32 cores per SM, 32 FP64 cores per SM, 8 tensor cores, 300 watts, so not 350, so 300 watt they draw. And then that's the peak performance that you get. About 7 to 8 teraflops, double precision, FP64. Twice that, FP32. 4 times that, approximately, FP16. If you can do away with that, usually for numerical applications, FP16 is not very helpful, but it can. And then there are these tensor flops, cores that give you an insanely high performance. So if you do machine learning, that will work very well on those. Deep learning will work very well on those GPUs as well. Any questions so far? No questions? Okay.
One question in the main.
Yeah.
Okay. You let them know, what is the difference between GPU core and CPU core?
Oh, okay. Well, I mean, a CPU core is basically an independent processor. And, if you have two cores, they can work completely in a completely independent task of each other. on a GPU, so you have this processor. In some sense, you can think of this processor as a core, and each of those, it's not true. Usually people talk about these individual cores here as a core, a compute core, but they cannot operate independently. All of those have to do the same operation at the same time. So they work a little bit like the vector units on a CPU core. So like the AVX 512 instruction units on a CPU core. In principle, the different multiprocessors, that's why they're called multiprocessors, because they have multiple cores, can do different operations, but usually you launch code that will run the same task on all of the multiprocessors. In some sense, you often do that also when you parallelize a code on a CPU, right? When you use OpenMP or MPI, usually you do the same task on all these cores, only, they don't have to operate in lockstep. And yeah, and the other difference is, of course, the CPU course, that's a CPU, and the GPU is just physically different. I hope that answers the question. Okay. I might be going too slow, or I'm talking too much. Let's look at some software examples. So we will go quickly through that. There are examples now from virtually any field, so there's not much to talk about. Lately, it's become very popular to do machine learning on GPUs, but you have any other applications, any other field, numerically intensive, data intensive, that runs and has some codes ported to GPUs. So quickly, just I mentioned this before. I don't want to talk much about machine learning because we have all these machine learning tutorials. There's different types of machine learning. The thing that particularly works well on GPUs, like I mentioned, is these deep learning workloads, right? So if you do something else like support vector machines or classification models and so on, they don't necessarily take good advantage of GPUs. They can, but not necessarily. But it's really the deep learning field. And the reason is, you have these neural networks with many hidden layers. And like I alluded before, is you have to do these matrix multiplications. That's basically these tensor operations when you compute when you traverse the neural network from your feature vectors from the input towards the output. There's all these magic multiplications happening from input to output, and the GPUs are really efficient at doing these. And if you think about the history, a 4x4 matrix algebra is used in 3D graphics, and so that's just naturally how the hardware has evolved. And then these half precision arithmetics can be used for many machine learning applications, right? So that's why half precision was implemented. And then now we have the specific tensor cores that literally in hardware speed up those tensor operations. And the machine learning frameworks, they provide GPU support out of the box. So you just have to tell PyTorch or TensorFlow that you want to use the GPU, and they will compile your neural network that you're requesting for execution on the GPU. And you don't really need to know much about GPUs. Of course, there are profilers and things like that, where you can actually profile the machine learning. There are profilers for PyTorch and TensorFlow, and you can look, can you change something in the ways you set up the neural network and similar things that can improve the performance. So you can do some tuning as well. Now let's just briefly look at benchmarks. And so you have to take those always with a grain of salt, because you've got to be very careful how people present the data, right? So if you're in salespeople like that very much, but sometimes if you look closely, the benchmark doesn't tell you much, so you really need to be careful, right? Here's an example of a quantum chemistry code that we developed. It's called Quick. It's open source. If you're a quantum chemist or interested in that, you can actually download it for free. A bunch of years ago, we edited a book about electronic structure calculations on graphics processing units. So, there's a bunch of different codes that have been ported that explain what they've been doing. So for Quick itself, you see, for different pieces of the calculation that we need to do, we get quite a decent speed up. So that's the speed up with respect to single core, right? So it's not like our code runs 200 times faster than a calculation that you would be doing, because usually you don't run on a single core, right? But maybe you run on 32 cores or 64 cores, and then you get on a single GPU at least the same performance or better performance. And that's what you see here. So that's a scaling plot where you see ideal scaling, and then those data points is the measured scaling of our code for two different operations for computing the forces, on atoms in a molecule. And this is the time on a logarithmic scale, right? So you start with 1 core, 2, 4, 18. This was going up to 40 cores that we had available on those compute nodes. And a single V100 is significantly faster, right? So that's basically the time that's taken by a single V100 GPU. So it's pretty impressive. And the expensive pieces that we do in these types of calculations, where we have to compute an energy functional of the electron density, and there's a piece in here that is, kind of resolved analytically. So we do a numerical quadrature over, where we have to evaluate this function here at the grid points, and we have many grid points. So just even for a small water molecule with 3 atoms, there's basically at the end, there's some grid pruning going on. There's like about 8,000 grid points, right? And then at each grid point, we have to evaluate, many of these basis functions, so-called basis function values, and so on. So what we implemented is basically parallel numerical quadrature that uses an octree-based partitioning of 3D grid points. So you have your grid points, and you start partitioning them into cubes and so on. So you go through this octree, and then you can do some pre-screening. You have these data points basically that belong to region of space. And now you can think about, we have all these individual compute cores. Of course, we have these grid points. We need to do this same operation here with multiplications and function evaluation at each grid point. Well, we can do this super in parallel, right? So this is perfectly to be parallelized. And so we do these operations on different compute cores, right? So this is ideal grid point batches that are being processed in parallel on different CPU cores, or if we have GPUs via CUDA on the different GPU cores. And then we have also parallelized the code across multiple GPUs. And if the computational problem that you have is large enough, so here is a small molecule, larger molecules, and so on, with many, many more atoms and basis functions, then you can see that then we have sufficient work that we can actually make use of more than a single GPU, right? And so the speed up is almost perfect, depending on the underlying size of the problem, right? So you can use multiple GPUs. Another example is molecular dynamics, where I've been working on a code, and I'm still working on a code that does also classical molecular dynamics, not with quantum mechanics, but simple interaction potentials. They're simple, but you see here atoms moving, and the whole enzyme here, in this case, it's an enzyme, and you see water, where we have to determine a water channel, exit channel in this from this reaction center in this enzyme. We have tens of thousands, hundreds of thousands of atoms, and we need to compute all those interactions between all those atoms. And the time steps that we are interested in, they are on the nano, micro, millisecond time scale. But each time step that we do in these molecular dynamics simulations, right? So in this movie, you've seen just a very short time, but those are many, many time steps, because these interactions between the atoms, we have to do the computation, and the time steps, numerical time steps for integration, the equation of motions is on the order of femtoseconds. So we have to do millions of time steps, and in each time step we have to compute all those interactions. And we don't want to wait years for the simulation to finish. We need to do these computations very fast, and we can do this very efficiently. And if you look at, so we had a code that's pretty well optimized for CPUs. You probably could optimize it more, but to get the gist of the essence here is the essence of it's basically here. 36 cores, single node, you get a throughput, a computational throughput. So you can simulate about like 2 or 3 nanoseconds in the life of a molecule that, like your cellulose in water, that has about 500,000 atoms. And on a single GPU, this is the V100 here, you can do about 20 times as much. Right? So that's really, really very powerful, enables a lot of new science. And the way we managed to do this is to implement a precision model. So this has different precision models in there. We're not now using this to make that does most of the computations in single precision and the accumulations in double precision. Actually, we use fixed precision, but that's just a detail. And it's important. I talked to you about precision and numerical accuracy, right? And numerical stability. What you see here is a simulation time and the energy. And the energy must be conserved due to Newton's laws, right? The energy is not conserved, something is wrong. And if you use single precision for everything, it's just numerically not stable, right? So you might look at the first few steps and your forces look okay, but then it starts to drift. And eventually your whole system heats up and blows up and the simulation breaks down. It's not valid. So you can do many things in single precision, but not everything. And you have to be very careful with that when you decide to do something like this. But because we have single precision, we can run on gaming GPUs very efficiently. And of course, also in the data center GPUs. Right. Any questions so far?
We don't have anything in the chat at the moment.
Okay, so I have a little bit of an overview now of GPU architecture. How we can speed up certain codes, examples that were very successful. And so what we're going to do now is we're going to start looking at how can we actually program GPUs. So if you program GPUs directly, there are different programming languages. So that assumes now you have a compiled programming language, or you could also have interpreted languages. You can have Python, for instance. We will focus now on C++ and C++ and Fortran. But there are different ways. There's OpenCL that you can use. I'm not going to talk about it, but this works for NVIDIA and AMD GPUs and other devices. CUDA, that's NVIDIA's solution. It works only for NVIDIA GPUs. It's the de facto standard for high performance code still. At least on NVIDIA GPUs, and it probably will remain like that for a while. There's something called HIP. I keep forgetting what it stands for. Heterogeneous. I don't remember. Interoperable performance. I don't remember. Something like that. This is AMD's answer to HIP, and that's an open source C++ runtime API and kernel language that is very similar to CUDA. So if you look at it, you literally you have all the same like instructions. I mean the same nomenclature, just a little bit different. And then there are a few things that are slightly different, right? So there's actually code translator where you can take your CUDA code, it basically does grab replace on CUDA function calls and definitions and so on, and generates this HIP code. And then you can use that HIP code, or you could write it directly in HIP. And then you can actually use that to generate back CUDA code or code for AMD's ROCm. So that's the Radeon Open Compute infrastructure. So HIP code, in principle, can get compiled for both NVIDIA and AMD GPUs, but you will not get the same performance as if you use CUDA directly. At least, yeah, that's probably. So it's a nice solution, but of course not perfect. We will focus on CUDA. And then there's OpenACC, which is accelerated directives for NVIDIA and AMD. There's not as much support for AMD simply because when this was developed, it was developed by the Portland Group. The Portland Group was purchased by NVIDIA, and they dropped the AMD support. But it's a standard being implemented also in other compilers. Now there's also OpenMP, that came from parallelization for threading for CPUs, but it's not only for CPUs. Since version 4, it includes accelerating vectorization directives, so these things are sort of like similar. I would say OpenMP is not yet as mature for GPUs as OpenACC, but we'll see how these things develop over the next few years. It's certainly interesting to look at all of those. We will look at OpenACC and CUDA. So this is an overview of the NVIDIA GPU computing universe, if you think about it. So, you have your GPU computing application. It uses libraries and middleware. And so there are many different libraries that are available, like QDNN, the Deep Neural Network library, 2FFT, as a T library, BLAST, for linear algebra libraries, sparse linear algebra libraries, and so on. There's lots of stuff available. It's also available through MATLAB and Mathematica.
Andy,
yes.
Mary here. I posted a link to the HIP, which is Heterogeneous Interface for Portability by AMD, and I posted a link to one of their articles about it in the Slack channel.
Thank you. Yeah.
Welcome.
Yeah, it's interesting to look at that. I'm not an expert with it, but that code, that quick code that we wrote in CUDA. So we have actually code generator that automatically generates code, and the complicated story because the code is so complex and complicated. We have Python code that generates C++ code with CUDA. And we have a hippified version of that, so people call it hippifying. So you take CUDA code and you turn it into HIP. But it's just a lot of work. So your CUDA code works out of the box, the HIP code doesn't. And AMD has a lot of catching up to do, I would say, with respect to. They have done lots of work, but they still have a lot of catching up to do. But of course, if you have AMD GPUs, HIP is the way to go. Or you can use try and see how well OpenMP works. I don't have experience with that, so can't really tell you much about it. Yeah, so programming languages: C, C++, Fortran supported Java, Python, wrappers as well, and direct compute, that's for graphics, obviously, and then directives, right? GPUs. Basically, you have CPU code, C or Fortran, that still works, both for CPUs in serial and in parallel on GPUs with those directives. And then, all of the GPUs are basically CUDA enabled nowadays. That's embedded hardware, the gaming GPUs, the workstation GPUs, and the data center GPUs. So if you have a laptop that has some sort of or consumer desktop, you can write code there, right? And CUDA is free. You can download it all for free. You can just work on your laptop and play around with that. So the CUDA SDK and the toolkit are free. It contains the C and C++ compiler. Well, it contains the CUDA C compiler. So it's NVCC, it's the CUDA compiler, and it uses the underlying system C and C++ compiler, okay, to compile the CPU portion of the code. Then it comes with all sorts of libraries. It comes with debugging tools, so CUDA GDB, CUDA memcheck. There's profiling tools. So NVProf and NVVP, that's a visual profiler. They're still in there, but they're being deprecated. So NVIDIA is really pushing their Nsight systems and Nsight compute to get an overview of the Nsight systems. Gives you an overview. So I'm not going into that, but it gives you an overview of the entire runtime of your code. How much time is spent on the CPU, when are your kernels launched, when are you running on the GPU, how much data transfer, and so on. And then Nsight compute is for each function. So each kernel, it's called a kernel. It's basically a function that executes on the GPU, a function that you wrote. And you can analyze that in detail about, the memory bandwidth, the data transfers, everything that's happening literally in that function. so that you have an idea how to optimize your code. Then there's lots of code samples that used to be in the CUDA SDK. They are still in the CUDA SDK, but there's also the NVIDIA HPC SDK that doesn't have code samples anymore. Instead, they are just on GitHub. You can just download them from this link. There are lots of information here on this link. Here's where you can get it. And then if you want to use CUDA and expands, it's pretty simple. You get onto a GPU node. What I like to do is to do a module purge and a module reset. You don't have to do that, but this is just in case, you know, you have set a module and it remained loaded. So something that might be CPU specific or different compiler and so on, and that interferes. So often it's good to do a purge, start with a clean slate, basically module reset that will load the default modules for the GPU nodes, which are different. So on the GPU nodes, you have different software available specific to the GPU nodes than on the CPU nodes. And then you say module load CUDA, and it defaults to CUDA version 11. There's also an older version. There's different versions available if you need that. Then we also have the NVIDIA HPC SDK, which basically replaces the CUDA toolkit. It contains most of the toolkit, including, you know, the libraries, the NVCC compiler, debugger, profiler. It also contains the NVIDIA C and C++ and Fortran compilers. They're called NV-Fortran, NVC, and NVC++. And those are basically the compilers that used to be PGI compilers. So those are good compilers. And you can get that for free from here. If you want to load the NV-HPC SDK, you just say module load NV-HPC instead. So, you know, if you have a C or C++ Fortran code, you know, there's three ways to use GPUs. Is use a library. If you already use a library, you just use the GPU accelerated version. That's basically perfect. You don't have to do much. You can use directives programming via OpenACC. That's an easy way to accelerate applications that are not too complex. And of course, you can do that also for very complex applications. But of course, it will take more time. Or you use explicitly CUDA as a programming language with maximum flexibility to get, you know, the highest performance out of the GPUs. Like I mentioned before, TensorFlow and PyTorch come with built-in GPU support, so you don't really need to know anything about that, right? So here's an example. Basically, there's actually additional ways. There's new things as well, accelerated standard languages. That's, you know, very recent ISO C++ and ISO Fortran standards, where NVIDIA's compilers can actually, you know, if you mention that you want to do something in parallel, for instance, here you have a loop, you can say do concurrent instead of just do an end-do, right? And the compiler will basically compile that code, offload it to the GPU, and do that in parallel for you. That's pretty fancy. That's something very new. If you have something like Python, you can use QNumeric, and it will do it will parallelize basically automatically, similar to NumPy. You know, it will use automatically fast libraries, and it will use automatically fast libraries on the GPUs. That's incremental portable optimization. So we'll look into more detail into that. It's, you know, OpenACC, you have these pragmas, and that you insert into your code, and then that compiler will basically, you know, in this section here says, okay, from here to here, I'm doing some optimizations, and will offload that to the GPU. Or you write the code yourself. You have these, you know, keywords and predefined variables that you use, and you manage the memory with memory copies, and then you launch the kernels with some sort of like specification here. The kernel is this thing here, and this will then run in parallel on the GPU. And I will try to tell you how this works. So we'll briefly walk through GPU-enabled libraries. And then we'll look at computer C programming basics, okay? So those are easy to use. You don't need to know much about GPU programming. It's a drop-in acceleration. Basically, the libraries follow standard APIs. There are minimal code changes required, and they are high quality and tuned by experts. So use those if you can. You don't want to write your own matrix multiplication because you won't get the same performance, of course, than something that has been optimized over the years by people who don't do anything else. So there's a wide range of libraries. Here's a link. Just take a look. Then there's something for every flavor of science to do. And here's an example where we're going to use the SIXPY BLAST function as an example. So that's a single precision A times X plus Y. So this is basically a vector addition operation. If you want to use QBLAST, you just call the QBLAST-SAXPY function instead. And then you have to do something else where you have to manage the data locality. You can use CUDA functions for that to allocate the memory and copy data from the CPU to the GPU and back. Or there are QBLAST functions for that. If you operate with vectors, there's a function for this that might make it easier for you to understand. And once you've done that, you just use the NVCC compiler and you link against the QBLAST library. Okay. And that's basically it. So here's this example of this A times X plus Y and store it back into Y. So that's the SIXPY function in the BLAST library. And so here's an example where you have n data elements. This is A, so 2 times. So what we're doing is basically Y equals 2 times X plus Y. And these are just the pointers to my arrays X and Y. I prefix them here with D because they wouldn't be prefixed, but usually when we write CUDA code, sometimes it's helpful to say, okay, this is a pointer to device memory. So we call device memory means the GPU memory. So we prefix it with a D to distinguish. But other than that, we just, instead of SIXPY, we call QBLAST SIXPY. We have to initialize the QBLAST library, create a handle here, destroy it again. Then we have to allocate memory. So we have to allocate here on these pointers. So we want to have now X and Y, those arrays, we want to have storage space on the GPU for those. So we allocate memory, and we have n elements, so n times the size of a floating point number. So we allocate basically n elements in those at this memory location, and then we use this QBLAST set vector function, which does nothing else than basically copying the content of X. So X, I assume here that we have X and Y on the CPU, in the CPU memory, and this just tells it, well, copy n of these elements from the CPU to the GPU, right? And then when we are done, we want to copy the result back as a QBLAST get vector function. And now we want to copy the result back from D, so our device, to our CPU, right? So we read the data back. And that's all that you need to do. And instead of doing that SIXPY operation on the CPU, it will copy the input data to the GPU, you run it on the GPU, and then you copy the output data back, and then you release the memory again. So that's what you have to do. And yeah, that's basically all, right? So in a similar way, you can use other libraries, and those will then effectively run on your GPU. The only thing you have to keep in mind is the SIXPY, you probably won't see a great speed up because this is actually not doing many operations. But if you do a matrix multiplication, that's a lot of computation that is being done in comparison to the data that you have to transfer from the CPU to the GPU. So you will see big speed ups, at least once the size of the matrix becomes sufficiently large, right? in this case, you'll spend probably more time allocating memory and transferring the data from the CPU to the GPU than doing this SAXPY function. Right? This talking about numerical computing in Python, I just want to mention that, if you're familiar, for instance, with NumPy, there's something called QPy, and it has an NumPy-like interface, and it's trivial to port the code to the GPU in this case. So, you have, this is highly tuned for CPUs, and so if you have code that you have NumPy code, it's very, very easy to get that over to GPUs, have the number crunching done on their GPUs, and there's data interoperability with deep learning frameworks as well. There's Rapids framework and Number, and it uses these highly tuned NVIDIA libraries. You can also write custom CUDA functions. I've never done that, so but if you know CUDA, then it can't be very hard. But here's an example where this is running, say, serially on a CPU. And this is just doing a QR factorization, I guess, of the it's a linear algebra basically package in NumPy, and I suppose QR is just doing a QR factorization of this matrix A that we have initialized here, so dimension 4096 by 4096. And you see how easy it is, right? You just say instead of NumPy, you use QPy. And that's it. It will automatically basically run on the GPU for you. And in this case, for this example, you get, well, it says for 52x speed up. So I got that slide from NVIDIA. And you'll notice, this is like with this benchmarks. Well, what does that mean, right? I mean, what GPU were you running on? What CPU were you running on? So I don't know. It could be anything, anywhere between 20 to 100x. I don't know, but it's going to run very efficiently on the GPU. Okay, so that's what I wanted to tell you about libraries. And now QC programming basics. Let me look at the time. It's almost noon. It will take me quite some time to go through those programming basics. So we have 1.5 hours left. And so we spent basically half of the time until here. I was hoping we were a little bit further, but let me get started with QC programming basics. And then let's take a brief break. Let's go for a few minutes, and then when I find a good spot, I will take a brief break so everybody can catch their breath. Okay, we might just make maybe a 10 minutes break. So you can get CUDA from, and get information here. So there's CUDA-C and CUDA Fortran, and CUDA-C and or C++ is basically a solution to run C and or C++ seamlessly in GPUs. And it has modest extensions, so it's not that hard to learn in some sense. There's not many things to learn, but there's much to learn about how the road code needs to be structured, and you need to think in, this parallel thinking, this data parallel thinking, and needs often major rewriting of code. And there are CUDA extensions in Fortran that were developed by Portland Group, and they are available in the NVIDIA Fortran compiler. Here's some recommended reading. If you want to know more, these are older books already, but still good, or you just Google, there's many resources here. The GPU hackathons, they're organized by OpenACC and NVIDIA. There's a lot of technical resources, a lot of information. The QC and Fortran programming guides are actually not too hard to read, quite interesting. So lots of information out there. So we're talking about the CPU and the GPU and so on a lot. So often you'll hear host and device, and what people mean is host that's the CPU and its memory. That is hosting that device, and the device is basically the GPU, right? And its memory. And so you write code that starts to execute on the CPU, so on the host code, and then it's launched from the host code. So how this looks like is, you have your serial CPU code. Of course, it can be MPI or OpenMP parallel as well, but in general, it's like serial code. And then you launch a kernel that runs on a GPU with many threads, and the threads, they are grouped into blocks, and those blocks are grouped into grid, and that maps onto the multiprocessors of the GPU, right? And then so you have this kernel launch here. So serial code, parallel code, and then you can do something serial again, and then parallel, and so that's typically how it looks like. So you have your host, the CPU, and its memory sitting on a PCI Express bus connected to the device. You copy your input data from the CPU to the GPU memory. So that's the GPU, which is its own memory. And you see here these multiprocessors. Each multiprocessor has many compute cores, has its own cache memory, and then there's this level 2 cache that caches data and instructions for all the multiprocessors. So after you've loaded the data, then you load the GPU program. So you launch your kernels, right? Or a function library call, right? Like the tubular Saxby. And it executes on the GPU. So you issue an instruction from the CPU that tells the, NVIDIA is called GigaThread Engine, but basically the scheduler on the device. Okay, now launch all these threads and operate on that data in the way that I've programmed in the corresponding function. And when you're done, you copy the results back. And so that's the workflow. I mentioned this unified memory that you can use. And that's the pooled memory that's shared between host and device. So that's a productivity feature. The memory copies, you don't see that. You just say, oh, here's my unified memory. And then you pass that memory to the CPU functions and to the GPU functions. But under the hood, of course, you still have the same hardware. So there's the data copy still happens. So you need to be aware of that. Right? And yeah, so how does GPU code look like in CUDA? Here's a very, very simple hello world. On the left-hand side, that's just C. So I'm working with C now here in these slides. I hope some of you may not know C. If you know C, then that will be trivial. This just prints hello world, right? And you can actually compile this. If you store this in a .cu file, that's typically the extension that you use for CUDA file. You can compile this with the NVIDIA CUDA compiler. What the CUDA compiler basically does, it separates the source code into host and device code and invokes the host compiler that can be, the GNU compiler, for instance, or the Intel compiler, so GCC or IPCC or the corresponding Fortran compilers if you had Fortran code, right? And then links everything together. And if you run that, you'll see hello world. And now if you want to do that from the GPU, now you do these funky things. You have a global __global__ keyword that indicates a function that should run on the GPU, but can be called from the CPU. Okay. This function doesn't do anything. It literally doesn't do anything. You can actually print from kernels. That was not the case in the past, but you can do that now. This is a kernel that's empty, so it really doesn't do anything, but you can compile it. And so you have this function myKernel, and now in your host source code, you can call that function with this funky nomenclature here, and that basically tells how many threads you're launching. So this is really not doing anything, but we've seen the syntactic elements about that function that runs on the device, but can be called from the host code. And NVCC separates, like I said, the source code into host and device components. And then, the device functions are processed internally by NVCC, and the host functions are processed, for instance, by GCC, right? The triple angle brackets mark a call from the host code to the device code. That's called a kernel launch. And, those numbers are the kernel launch configuration that basically say how many threads I'm launching. Okay, so this kernel doesn't do anything, but let's try and do an addition on the device. So how would we do that? So now you see this is the function, our kernel. We call it add, and now we are passing pointers to memory, A, B, and C. Well, we just do an addition, right? So C equals A plus B. So because this is a CUDA-C word, a keyword, add will execute on the device, and it can be called from the host. So it executes on this device. Obviously, A, B, and C must point to device memory, right? So how do we do this? We have host pointers that point to CPU memory just in your normal C code, but we can pass them to the device code. So we can pass the pointer address, right? We cannot dereference them. We cannot use them. But then we have device pointers, so basically pointers that point to memory locations on the GPU. And again, those cannot be dereferenced in the host code. And then we use the CUDA API to handle device memory. So we can allocate memory, CUDA malloc, that's equivalent to malloc on the CPU, CUDA free, and CUDA memcopy that handles the transfer of data from the CPU to the GPU and back. Like, you've seen that already in the SI22 example. And then, that's the equivalence to the corresponding C functions. So we have this addition, and so now here's a lot of code, but don't worry. This is data that we have on the, so I prefix it with H to say host and D for device. So we have A, B, and C, those are three integers. They exist on the CPU. And these are pointers, right? And what I do now is, well, I want to have integers, so I define the size here, a size of int. I allocate memory on the device, right? So I use the CUDA malloc function, and I get back a pointer to memory that has been allocated on the GPU, and there's a certain amount, in this case, just a single integer that's allocated. So now I have DA and so on, DB and DC point to the memory address of an integer on the GPU, right? So let's assume we have some input values. So this is data on the CPU. Now I can copy the input data to the device. I use the CUDA memcopy function with this option here, CUDA memcopy host to device. So I want to copy from host to the device. So it's the target and this is the source, right? I do this for A and B. And now I have A and B on the GPU. Now I can launch my kernel. So I call this add function and I just launch a single thread because I have only a single number, right? And when I'm done, I copy the results back. So now I do a copy device to host. So from this device pointer back to the host, and I can free the memory and print the results. So this way we've done something very convoluted to add two numbers, but the addition actually happened on the GPU, right? So that's the basic CUDA workflow. You allocate memory on the device, copy input data to the device, launch a CUDA kernel on the device, and then when you're done, you copy results back to the host. And then you deallocate memory on the device, okay? Let me see, let me check my slides briefly to see what's coming. Vector addition. Yeah, we've been going for a while. Let's take a brief break now, and then I'll walk you through. Let's meet back at 12:15, okay? And then I'll show you basically on parallel computing on the GPU using CUDA. And if there's questions in the meantime, feel free to ask. Are we recording or is it?
Yes.
Okay. Oh yeah, I can. No, yeah. I thought I'd see some notification. All right. Well, welcome back, everybody. Hope everybody can take a brief break. So, we've learned on, how we can load data onto the GPU and do a computation on the GPU. That was just a single addition. But of course, we want to do this in parallel. So let's move on to parallel computing. How do we run our code in parallel using CUDA, right? So it's all about massive parallelism, and massive parallelism because, you know, we have thousands of threads that we need to launch, so much more than on what we used to from CPUs. Well, instead of executing the kernel at once, we just execute it n times in parallel. So if we have a problem that is data parallel in a sense that we need to do the same type of operation, that is an addition, multiple times on different data elements, then we can parallelize it, okay? And so that's the central idea that defines GPU computing. So the kernels effectively look like serial programs. We write the programs as if they run on a single thread, but we keep in mind that it's being executed by many threads on different data elements, right? And so the GPU will do that for us. So, and that we do with the kernel launch configuration. Instead of launching one copy, we just launch n copies. So these are actually the number of blocks. There's a reason for the number of blocks, and these are threads per block. I get back to that, but the GPU is good at effectively launching many threads, many more than processors on the device. And so again, why n identical copies of the kernel doing the same operation, right? That's if you have something that is basically inherently parallel, like a vector addition, for instance, as the most simple example. You know, you see on a CPU, in serial, basically you go from element to element and do the addition. So you have a for loop in there. So that for loop, you know, ideally you could parallelize it where, you know, you just do each compute core will operate on a different data, and, you know, there's an addition of the first element, the other core does it on a second element and so on. So this is how our first version of a parallelized add kernel would look like. So there's a built-in variable in CUDA that's called block ID x.x, and you know there's an x here because you know this can have multiple dimensions. So if you say have a two-dimensional problem like a matrix, or a three-dimensional problem like a grid in 3 dimensions, you know, or say I don't know, like we had in the quantum chemistry example, or say a weather simulation. Then it might be helpful to have a 3-dimensional indexing. And so when this kernel launches, you know, it knows its ID. It knows whether it's ID 0 or 1 and so on. And so we can define a variable where we assign the ID, and then we just let that thread with this ID being operated on that corresponding element in the array A, B, and C. Okay. So by using its index, each block operates on a different data. And so we basically launch n copies, right? So this is literally how it looks like. So block 0 operates on element 0, block 1 operates on element 1 at the same time, and so on. Now, this is not very convenient because the kernel call, I mean, first of all, this is always true. The kernel call needs to be consistent with the kernel implementation, right? If I put an n here, the kernel itself must be written such that, you know, I have n beta elements that I'm operating on. So this is how the entire code looks like. So this was the kernel I just showed you. And now instead of doing an addition, I do a vector addition. This is the same as I showed you before, but instead of A, B, and C as numbers, I just have an array here, right, with n numbers in it. And now I'll allocate basically a pointer to the device memory that has n, you know, for n numbers. And let's assume I get my input data from somewhere. That's, you know, my input vectors A and B. And now I want to do the vector addition. I do the same thing. I copy the vectors now from the host to the device with CUDA mem copy. And then I launch n blocks instead of just a single block, right? So this way I can do 512, for instance, like in this example, I had set n to 512 hard-coded, right? A vector addition on the device, on the GPU in parallel. This is still not great, right? This is weird, but I can also use threads. There's a different variable that's called thread ID. And that basically indexes that second number here in the kernel launch, right? So again, you know, this implementation needs to be consistent with how I call the kernel. I can do the same thing, and then I can combine blocks and threads, right? So I need to take care of the indexing. That's the important piece, right? So CUDA supports 3-dimensional blocks and threads. The number of threads per block and the number of concurrent blocks that you can run is limited by the hardware, right? So there are up to 2048 threads per block on current GPUs. Why threads and blocks? So the threads and the blocks, they map to the underlying hardware. Okay, so you've seen the multiprocessors before. So all the threads in a block. So if I have n threads here in a given block, they all are guaranteed to execute on the same multiprocessor, the same streaming multiprocessor. So they share resources. They can actually communicate to each other via that shared memory, right? Threads in different blocks can not communicate with each other, right? One thing you have to keep in mind, even if you see these examples now with less than 32, but I talked about this warp size. And because the scheduler issues instructions in multiples of warps, you must have a multiple. You should have a multiple of 32 here as thread size. Otherwise, you're going to waste resources. Because, you know, say if you have 33 here, then you would have 32 cores doing an operation, and then you have one more thread, but it still would issue the instructions to 32 cores. That means that 31 cores would do nothing. They basically are just occupied doing nothing. So you need to use a multiple of 32 here. So, you know, let's assume we have an array and then we have multiple blocks. So this is an example where I would launch 8 threads per block. And now I have an array that has a length of 32, just for, you know, being able to explain this on a slide. Then, you know, what I would do is I would launch 4 kernels, for instance, a kernel with 4 blocks. And you see the threads in the first block, they should operate on the first 8 data elements. The threads in the second block, they should operate on the second 8 data elements, and so on, right? So there's a built-in variable blocked in that contains the number of threads per block. So that's the block dimension, right? So I know the number of blocks, I know my block ID, I know the block dimension, I know my thread ID, and with that, I can calculate a unique index, right? So for instance, if I want to know which of those individual threads that has been launched that's running this kernel should do the addition of or operate on this data element there, well, I want to be in block number 2 and thread number 3 should do that, right? So I just say, well, my global thread ID is just my thread ID plus my block ID times the block dimension, right? So 2 times 8. So I'm block 2, right? And each block has 8 threads, so the offset is basically 16. So those are the first 16 elements plus 3 because I'm thread number 3, so I should operate on this data element 19, right? So this is basically 8, 16, 17, 18, 19. That's correct, right? And so that's how you index, compute the index, and you can know what you should operate on. So you say my thread ID is now thread ID x.x plus block time x times block ID x.x. And now you have now you can launch a kernel, and all you have to make sure is that you launch a certain threads per block, and then you use a number of blocks that is basically such that, you know, the threads per blocks times the block number sums up to n, right? So this is of course a limitation. So what you want to do is actually launch at least as many blocks as are required to operate on all elements of our vector n. And then we need to pass that information to our addition function, to our add function, and then we just put an if statement in there and say, well, if my thread ID is less than n, then do this operation, otherwise don't do it, right? So this way I can have a size of a vector that's not a multiple of our chosen block dimension. few threads will do no operations at the end, at the end of the vector, but that's fine. It's just a little bit of resources that are being wasted, but not much. So we write a kernel that looks like it runs on one thread, but we launched it multiple times, multiple threads per block, so multiple blocks. And then each thread knows its index in the block and the grid. And we can use that to compute a unique thread ID. And now we want to do that to handle arbitrary vector sizes. And because the maximum grid and block size is limited by the hardware now, if you have a vector addition of, I don't know, 1 billion elements, how do you do that, right? So what we always want to do is we launch a fixed number of blocks and threads. And that fixed number just depends on the hardware you're running on, depends on how many multiprocessors you have and so on. And so we rewrite our kernel for fixed grid and block size. And we can do that by using another built-in variable that knows the number of blocks in the grid, so we can know how many threads in total we have running. And with that, we can compute strides. So, our threads, they operate, imagine you have n threads, so they do the addition on n data elements, and then they skip the first n data elements, operate on the next n data elements, and they keep doing this until they reach the end of the vector. Okay. And yeah, so for many kernels, the performance is optimal for a certain GPU hardware-dependent combination of grid and block size, and that's just something you might have to experiment with. And so you query the hardware at runtime for an optimal kernel launch configuration. So yeah, I don't think we need to go a lot into details, but basically, the grid dimension is, if you had only, this is the example where, I have this 32 data elements, but instead of using 4 blocks, I only launch 2 blocks, right? The orange one and the blue blocks, 0 and 1. So the first block operates on first 8 data elements, the next block and the next 8 data elements. When they are done, well, the first block goes to the next, and the first block here on to the next data elements. And then they're gonna check, is there anything else to do? Nothing is to do, and then they'll stop, right? And I just do this with an if statement. So I need to know the stride, I call it the stride, that's basically how many threads I have in total, right? It's the block dimension times the grid dimension. And then I just do a loop here and I say, well, while my thread ID is less than the size of the vector, which I'm passing to my addition function here, I'll do this vector addition. I do this addition. And then I increment my thread ID by the stride. So I'm looking, for instance, if I'm thread 0 in block 0, I'm looking at this data element. And then I skip. I'm operating on this data element. Then I skip. Well, and now my thread ID is larger than n, so I'm going to stop. Right. This way we can launch a fixed number of kernels. This shouldn't say a fixed number of kernels, a fixed number of threads per kernel. Okay. Yes, 3-dimensional indexing, I mentioned that. So you have these DIM3 variables. Not much to talk about. And, those are the variables that you have available for indexing in QDAP. And so now there's lots of material in the slides, and we're going to skip that because we don't have time to talk about this. But I think we don't need this. It's just some, more information. And let me find the slides where I wanted to continue. Oh, where's my pointer? Oh, here it is. Skip to this, right? Okay. So what we've learned is we have a kernel that is code that can be executed on the GPU. That code, when it's executed, operates in lockstep on the multiprocessors of the GPU in so-called warps, which are multiples of 32 threads. So it's basically a single instruction executed by multiple threads, the SIMT architecture. A thread is basically an execution of a kernel with a given index, and each thread uses its index to access a subset of a data, say an array to operate on. And the threads are grouped into blocks which execute on the same multiprocessor. Because that's the case, they can synchronize data. So I'm not showing this, but there's some information about that in the slides. And then the grid is all the threads, all the blocks that are running on the GPU. And from that you can get an information about the total number of threads. So here's an example, right? You have that grid, a certain number of blocks, and each block has a certain number of threads. That's pictorially how you have to think about this, right? We have distributor built-in variables that I talked about for the grid dimension, block dimension, block index, block dimension, and the thread index in the block. And for this example here, which looks sort of like crappy graphics, that's actually just taken out from an old CUDA the language, CUDA language guide. But yeah, it would be 6 blocks, 3 times 2, so two-dimensional, right, and 4 times 3 threads per block, so a total of 72 threads. Of course, in practice, you're not going to do something that always have 32 multiples of 32 threads per block. That's just for illustration purposes. And we have that global keyword for a function that executes on the device. There's also device functions. And with a global function, you can call that actually from the CPU. And we have those. CUDA API has a lot of other functions, to handle memory and just look it up in the CUDA guide. And then the CUDA kernel launch configuration, that's in this triple angle brackets here, this chevron notation. Yeah, so that's what we've learned so far. Here's some more information about how the memory relates to each other. Okay. So if this is the GPU, so the grid that I talked about, all the threads, they're running on the GPU. So they have access to global memory, right? They also have access to something that's called constant memory that can be set from the CPU and read during the execution of the kernels. So you might want to store something like pi in there, right? Or some parameters for the simulation. And then you have those blocks, they run on a multiprocessor, so they can access their shared memory. And then you have the individual threads that have access to the registers when that's automatically generated when the code is compiled, right? There's also something called local memory. So once you run out of registers, it's not really local. It's thread local in a sense that only the thread can see that, but it gets stored actually in global memory. That's when you spill basically out of your registers. The compiler does this automatically, and that significantly slows down your code. So that's where you will have to do some profiling and use the Insight tools, Insight Compute, to understand what's happening in your code and to optimize it. So that's an important thing. So when you program, you want to avoid data transfers between the CPU and the GPU because the PCI Express bus is slow. You can hide memory access latency, meaning, getting memory from this data from this global memory by launching many threads. And then you can take advantage of fast shared memory by tiling data. So I'm not talking much about this, but this is basically same as cache blocking in CPUs, right? So you basically load the data, store it here in shared memory, and then all your threads, if they have multiple times that they need to access the data, they can do this very fast because this is very fast memory. And then you have this constant memory that you can use that is very efficient if multiple threads need the same data. And so there's a matrix multiplication example that I'm going to skip over because there's no time actually for us to look at this. But what that example, oops, where's my pointer? I lost my pointer. What that example is doing is it makes use of two-dimensional grids and blocks and shared memory and thread synchronization. And there's some optimizations in there, and still it's much slower than the highly optimized BLAS library. there's some information about atomic operations to avoid race conditions. And there's an example in there as well, and I have that in the source code. And I will skip over this because we want to do some hands-on sessions, okay? And so we're going to skip to accessing GPU nodes and running GPU jobs and SDSC expands. And I want you have a little bit of time to explore this yourself. We have a good amount of time until 1:30. So, but I don't want to spend too much time because I also want to introduce you to OpenACC and have some hands-on exercises for that as well. So what I will do is I go through some slides now, and then there is specific information also on the GitHub website, okay? So I'll just walk you through this, and you'll have all that information on the GitHub website as well. You know, once you log into Expanse, you know, you get onto the login node, obviously, right? So we know that. Then just as a background again, so the GPU nodes, we have two different partitions on Expanse. So we have a GPU partition that gives you access to entire GPU nodes. So you'll get 4 GPUs. So you will have to have a code that actually makes use of 4 GPUs. And then there's a GPU shared partition where you get access to individual GPUs, right? So those, you know, if you had a batch job, you'd have the option to use the partition GPU or GPU shared. In addition to the partition name, you must specify the number of GPUs. So for us to access the GPU nodes, you know, you don't have to do this. So there's an alias defined, but I just want to show this to you. And so if you try yourself and if you have an allocation and so on, so you know how to use that. So for an interactive access, for example, you know, you would be issuing a command that looks like this, and we have an alias for that, for the specific reservation as well. You use the GPU shared partition on a single node. We want 1 GPU, and now we want 1 task. That's a CPU task per node, and 10 CPU cores. Like I mentioned, you know, we have 40 CPU cores on a GPU node. So if you ask for a single GPU, you shouldn't ask for more than 10 CPU cores. Otherwise, you will be charged for using 2 GPUs because, you know, somebody else wouldn't be able to use these cores that are, you know, sort of like proportionally belong to a different GPU, right? And then you have that's a CPU memory. Again, don't use more than a quarter of the available memory. And, you know, then SRun would basically go ahead and Slurm allocate a node for you, and you'll get onto an Expanse compute node that now would have a GPU. So yeah, so if you make requests yourself, you know, you should do that proportional to the number of available resources. And those are the resources on a GPU node, right? So if you use only 1 GPU, use 10 CPU cores and not more than a quarter of the available RAM. I think 93, I would just not use more than 90, just being the safe side. So you can try that yourself now. I'll have a few more slides that I show you, and then I'll go to the GitHub repository and show you what you can go through and try out. So if you should have this command available, srun GPU shared, and that should give you interactive access to a shared GPU, a single GPU and a shared GPU node for 4 hours. Yeah, if you try to get access to an Expanse GPU node now, and let us know if that doesn't work, which I hope it works for everybody. And then you can do, you don't have to, but yeah, maybe just do a module purge and module reset. This is SDSC specific stuff. Yeah, you can also load that. It's not really required for using CUDA, but doesn't hurt. Then you can load the CUDA toolkit. You can load the PGI compilers, or you can load the NVHPC SDK. So if you load NVHPC, don't load these the CUDA toolkit or vice versa. If you are on a GPU node, then you can issue the NVIDIA SMI command. That's the system management interface. And it will tell you some information about the installed driver, the CUDA version, and then the GPU. So you'll see something like, okay, there's a Tesla V100 SI22 GPU. It's currently using only 67 watts of 300, so it's probably idling. And yeah, it's idling because, you know, there's no memory allocated, so it has still 32 gigabyte of memory free. It's also pretty cool. It's only 45% centigrade. So if you run a code on it for a longer time, that temperature will go up, right? And, you know, it should show something like no running processes found because, well, there's no process currently running in the GPU. Otherwise, you know, if you have a job running on the GPU, you'll see the name of the process and it's which GPU it's running on, and then the process ID and so on. If you have CUDA loaded or NVHPC, then the CUDA C compiler should be available. So NVCC, you can issue NVCC -- version. Same for the PGI compiler. And oops. Yeah. So and then we'll go through the exercises. So this is accessing the GPU nodes. So let me just quickly I guess I should increase this size here. Right, so if you go to the Summer Institute GitHub repository, first of all, clone it. If you clone it on SDC Expanse, you'll have the CUDA samples available. So we have this, you know, this is the Summer Institute GitHub repository. Okay. And here 5.2a is the GPU session. Okay. And here's the README file. So this has the information I was just talking about, accessing the GPU nodes and running jobs in SDC Expanse. So you can go through this information on what you should see. And then there's information about the hands-on exercises. Okay. So literally we'll do those now. I'll give you some time, maybe say 10 minutes or so. Maybe until 1 we can do that. You know, 15 minutes should be a nice amount of time. You can go through this and then compile and run the matrix multiplication examples and so on. I will show this on slides to you, but you have in and output here, and you will recognize all of that from the slides. I'll just go through the slides because that's easy to show. So the CUDA toolkit, right? So it's available from NVIDIA and it's also station in Expanse, but don't copy everything. It's a lot of data, just takes a lot of time, right? But I have that select examples here in the SDSC Summer Institute GitHub repository. So if you've cloned that, if you cloned it before, do a git pull to update it, right? So because I uploaded the slides and some of these things last night, then there should be a directory 5.2a GPU computing and programming NVIDIA CUDA samples. So those have select NVIDIA CUDA samples, and either you can compile them all if you go into that directory, and this option SMS equals 70, that's just the 7.0, that's the architecture of the V100 GPUs. Or you go into specific example subdirectories, and there is a device query example, and that's very, very, very interesting because so this basically queries information about the GPU. So that's like what I said, you know, you can use CUDA functions to query information about the GPU. And if you look into the source code that's in there, you know, you can see how that is done. So it's interesting to inspect those source code examples. if you run that, it gives you information about the GPU. It tells you, oh, what type of GPU it is, the CUDA capability version, the memory, the cores that are available, and so on. So a lot of interesting information about the GPU. The other example is the matrix multiplication example. So there is a hand-coded matrix multiplication that has a lot of optimizations in there, like cache blocking and so on. And it measures the performance that you get. And it's interesting. So run this. So remember, we had about 7.8 teraflops. So 7,800 gigaflops. And we're getting only about 3.2 like that, right? Now, if you go, there's an example that uses QBLAS library. If you compile that and run that, you'll see that you get very, very close to the peak floating point performance. So you know, that basically tells you, yeah, use the QBLAS functions, for instance, if you can. And then there's a different directory here in the subdirectory that is called CUDA samples. And this has these hello world, the addition, the vector addition, and then the squaring matrix elements and 1D stencil that we didn't discuss. But if you want to go and come back after the Summer Institute and read up on this and try those out, feel free to do that. Check the README files in there. There you can compile and run those examples. Those are very simple examples. And there are also exercises in there that basically I just deleted some things and said, okay, can you figure out what you need to put in there to make the code run correctly. So yeah, let's do this until 1 p.m. You can follow these examples here. They're explaining exactly what to do. And we'll stop once you get to OpenACC. And so I will continue at 1 p.m. to talk about OpenACC. In the meantime, if you have any questions, I'd be happy to answer those.
Andy, we have one question in the help desk. Anna? I'll let you look at that, command not found, and possibly with your examples there, it's answering that question, but I don't know the answer.
Okay, let's see. SRAM command not found. Oh, that's crazy. Oh. Okay, let me share the entire command. Let me just log in. But srun.command not found. Are you on the login node? No, it is the login node. Oh. So here I am on the login node. So this would be the command. Let me copy. Copy this. Oops. Put this in Slack. See if this works. If I do this, let's see what happens. So I got onto a GPU node. Oops, module, I wanted to say module purge. Is it default? I keep forgetting myself. I actually did. I think it's. No, modular reset. So, yeah, so this already loaded the. Do you have the Slurm module loaded? So that is for. So for Anna. Yeah, but that should be in the login node. I don't know. Anna, if it still doesn't work, maybe we need to ask Mahida or Martin. So if the GPU module is loaded, then you can load, you can also check the module available. You should see, NVHPC is available, and by default, this one will be loaded. Or if you load the CUDA module, you'd have, by default, this one. Let me load NVHPC as an example. So now I have NVCC available. And yeah, spits out the corresponding version. And then there is, of course, also the NV Fortran, for instance, NVIDIA Fortran compiler. And yeah, so NVIDIA SMI shows, I have a GPU available here. And there's nothing running at the moment. And let me go back. I think there was another question. Okay, so the question says, I would like to know if the code can be run both on CPU and GPU. Now the question I have, yeah, I'm not sure exactly what you mean with that. So usually you have a code that often you start with code that runs on the CPU, and then you rewrite parts of it to run on the GPU, so the compute intensive parts. So you still will have code that runs on the CPU, but it has to be compiled differently, separately. It's different executables. Now with compiler directives like OpenACC, you have basically a CPU code, and you can compile it either, and then you add these compiler directives, the pragmas, and you either compile the code taking those pragmas into account, sorry, my audio just dropped, I think. Can you still hear me?
Yes, we can.
Yes.
Okay. So I was talking about OpenACC. So you insert the pragmas into the source code, and then you can compile it. And the pragmas are basically in comment lines, and the compiler for the CPU will completely ignore those. So you still have your CPU code. And then you can compile a different version where you tell the compiler to take those pragmas into account, and it will generate code that then will execute partially on the GPU. I mean, those regions where you told it that should run on the GPU. So in some sense, you can have source code that, yes, is able to run on the CPU, and if you compile it differently on the GPU, but I mean, you don't have the same executable that will do the same things. So one and the same executable will not run on the GPU and the CPU. But of course, like I showed you, usually you have some sort of like code that runs on the CPU, and then it will call the functions to be executed on the GPU. So it's always a little bit of a mix. You always need a CPU. Okay, there's an error here. Cannot find minus LQ plus. Ah, okay. So Pam has a error, and I think what's happening here is if we're going through those exercises, compile and run matrix multiplication with the QBLAST library. Did you do these export commands here? So this is I would say an oversight of how NVHPC was installed by Bright Cluster Computing on Expanse. These should be automatically added to this path and the the library path and the linker paths, but it's not been done, so we have to set this manually. So the problem you see is probably, let me see, let me do this myself, right?
So that fixed it.
That fixed it. Awesome.
Fix it. Thank you.
Yeah, so usually you would expect that you log NVHPC and this is all set correctly. But yeah, unfortunately, that's not the case.
Andy, do you see the question in the help desk from Kyle?
Oh, sorry. I went back to my slides, so I hadn't monitored that. NVCC command not found. Okay. So did you load the NVHPC module? This will not compile with the CUDA module because it requires it requires a higher CUDA version than the one that we have installed, because they made some updates to those NVIDIA samples that actually would compile, but they build files, they make files, they're checking for certain things that is only available in the newer CUDA version. But with the NVHPC, it should work. So if you do a module list, if you have, Kyle, check if you have NVHPC loaded. Yeah, so Kyle, if you do NVHPC, And then so if you issue nvcc -- version, you should get this output here. And then in addition, you need to do this export command. Again, this has to do with the version of the CUDA samples, NVIDIA's CUDA samples. Okay, I assume that most of you had a little bit of a chance to play around with that. Perhaps compile all those examples that I mentioned here. And so we have about half an hour left. So let me go to OpenACC, explain to you what OpenACC is. Give you a brief introduction to OpenACC, and then hopefully we'll have another 10 to 15 minutes to play with that. I'm always overly optimistic with respect to time, so I hope we have enough time. So OpenACC is directive-based programming, and it's an open standard for expressing accelerated parallelism. So what that means, it is a standard. It's being adopted by different vendors, not only NVIDIA, right? So in some sense portable, and it's designed to make porting to GPUs easy, quick, and portable. Right? So easy means you don't have to write these CUDA kernels. Quick, yeah, it's faster because of that, and then portable, it should work on different generations, but also different GPU architectures, because in principle, the standard doesn't say it has to be a CUDA capable GPU, right? And it's OpenMP-like compiler directives. If the compiler doesn't understand the directives, it will ignore them. So you can compile your code still with your whatever favorite CPU compiler. So the code can work with or without accelerators. It's available for Fortran and C. It's fully supported by the PGI compilers, Cray compilers and Crays. There's a partial support by GNU compilers, but they're also, of course, going into OpenMP direction. Yeah, so really the most mature compilers are the PGI, or nowadays basically the NVIDIA compilers. There's also OpenMP, but it's not yet as mature for GPUs, and I don't know much about it. I have never used it, so I will also not discuss much here. I mean, I've used OpenMP, but not for offloading to GPUs. So there's a PGI Community Edition available under this link here, but it's been replaced by the NVIDIA HPC SDK. So, you just get the NVIDIA HPC SDK. You can still load, though, we have the PGI modules on Expanse if you wanted to use those. And here's a simple example. So remember, we've been talking about vector addition and SAXPY, which is basically vector addition with some additional, multiplication here of the scaling of one of the vectors. And if you were to implement that in serial, right, we have an example in Fortran on the right and in C on the left. You just have a for loop or a do loop, right? That does just this vector addition. And so you could write this function here, right? Instead of using a BLAS library, of course, you would use a BLAS library, but let's assume there is no BLAS library, you would write that function yourself. And that's what it does. And now, instead of, writing a CUDA kernel and, like this vector addition that we did and doing the memory copies and so on, well, all you do is you insert a pragma ACC kernels here, or you have a region here, ACC kernels and ACC end kernels in Fortran, and that's it. And now it should magically work on the CPU. And so it does, right? So here's the entire code. So here's our SAXP function. It has the pragma ACC kernels here. So it really tells, okay, OpenACC generate kernel for this loop. okay, for this region. So it's inside of this region of, delimited by the curly brackets. So it will try to parallelize that. And this is the entire program. This is just the main program where, we're just setting some input values here. And then we call the SAXP function, right? If you have the Portland group compilers, so there's like PGCC is the C compiler, PGF90 is the Fortran compiler, the Fortran 90 compiler. Now, if you just use PGCC or PGF90 on the C or F90 code, without these options here, it's just going to generate the code for the CPU. Now, if you say -ACC, it tells the compiler, oh, there are open ACC pragmas in there. So do interpret those and generate code for the GPU via open ACC. And then you have to define a target architecture. So Tesla are basically the data center GPUs. So you tell it to use Tesla. So you probably can leave that off in the newer versions of the PGCC compiler, or then the NVIDIA's compilers, the NVHPC SDK don't require these options anymore. But you have to say -ACC, right? And then this is just from information. So you're requesting some information about what does the compiler actually do when he accelerates the code, when he generates basically the GPU code. So if you issue that command, it will give you some output because you requested this information, and it tells you, okay, there's in line 8, it generates a copy in, and it generates a copy of Y. And in line 9, it recognizes, oh, this loop is parallelizable, and it generates an accelerator kernel. So it generates that kernel for you, generates Tesla code. And so for line 9, it gives you some more information about, the loop vectorization with the gang and vectors. And so that's basically what maps to threads and blocks. So when you see, these are basically block IDX and thread IDX. So what it did is actually it generated code, and by default generated code with a kernel launch configuration of 128 threads per block. And remember, X is an input, Y is an input, or Y is also an output of the function. So it copies only X to the GPU, but not back. And for Y, it copies to the GPU, and when it's done back. So that's the copy in and copy function. So it seems to do all these things automatically. And then, of course, there are many, many more directives that you can use. And like, you've seen it now. Okay, I've switched, and left is button and the right is C. So you often have these directives with optional clauses that you can add. They are followed by a structured code block. And in Fortran, you often, you have to pair them with a matching end directive. So surrounding a structured code block like that for do loop, right? Otherwise, it doesn't know where to end. While in C, you have the brackets, so, curly brackets, so it knows where that ends. And there's a kernels construct, right? So that's the one that we use, pragma ACC kernels. So you see it's followed by a structured code block here, or you have the code block here in between the ACC kernels and end kernels pragmas. And yeah, so and then you can have clauses, and the clauses can, you can have if statements there, right? If a certain condition is used, or, for asynchronous execution, or data clauses. So let's look at data clauses. Data clauses, you can use copy, and then the list is a list of it's a list of variables, arrays, or that you want to copy. Copy means, allocate memory on the GPU, copy data from the host to the GPU when entering that region, and copy the data to the host when exiting the region, and then deallocate it. Copy in means just copy it in, but not back out, right? So those were the two things that you've seen that the compiler automatically did. And then copy out means just copy out, right? So that's basically just output data. Create means basically allocating memory. Present means, okay, and this region, when we hit that region of the code, those variables are already present on the GPU. So don't just use those, right? So you could imagine that you have different regions of your code where you have a larger code that's not just a single function, right? And you basically allocate memory somewhere, and then you do some copy operations, you generate data, you compute something, and then you hit another region that you also want to parallelize, and that data is already present. And so those are things that you can tell OpenACC. And let's look at an example. And I have this example, the SI22, and this example, they are in the repository for you to play with and test it. Just as a background, what this does is basically for solving Laplace equation in 2 dimension, that's heat equation, or there are many different algorithms that use this type of operation. It's really a stencil operation where, in this case, we have a 2-dimensional grid, and we have starting values, and then we do an iteration. The iteration here is an index k. So our next iteration at step k plus 1, we want to compute the value is basically an average of the neighboring values. Okay, so you see we need to look at the neighboring elements to the left, to the right, to the top, and to the bottom, and then just divide those by 4. So that's what the algorithm does, right? This is the C code, right? So we do this iteration until basically between 2 steps, the value of this matrix element A or this grid point doesn't change anymore within a certain threshold. So we have a while loop here, okay, where we iterate as long as our error, so the maximum difference between the current and the previous iteration, is larger than a threshold tolerance. And while we haven't exceeded our maximum iterations, so we can say, okay, do only 1000 iterations, then stop, right? So we set an error to 0, and then we have this double loop, right? Where we go just through each element, I and j, and we compute the new element as the average of the neighboring elements, right? And then we look at the error, we update the error as basically the maximum of the new matrix element, or grid element minus the previous one. Okay. When this loop is done, all we have to do is we need to swap the input and output arrays. This is sort of stupid here because really we just need to swap the pointers, but that's just for illustration purposes for OpenACC. So in reality, you would just swap the pointers here. You don't need to really copy the data, but here we're copying the data basically from the new output array into the previous one, and then we increase our counter and we do this whole thing again. Now, great. This is a double loop. I do something in the matrix. Let's just do this in parallel on the GPU, and then let's do this also in parallel on the GPU, right? So pragma ACC kernels, like in the SI22 example. Great. Now we compile this, and you can use the Fortran version. In the example, there's a Fortran version, and there's also a C version. And you'll see what it does. It generates this copy out, copy in, accelerator kernel generated, and so on. You get all this information. So it generates 2 kernels for the 2 regions here, right? For this update, the Jacobi update, and for the swap, the data elements copy operation. Okay, well, let's run this. These are all timings, so if you play around with that on Expanse, you'll get very different numbers, of course, right? I have an OpenMP version of this, and so this was the predecessor of Expanse, and so, okay, 1000 iterations took like 69 seconds for the whatever matrix size, the grid size that we have. You get a speed of about 2 when I use 2 OpenMP threads, 3 and 4, with 4 and 6 OpenMP threads. So at some point it becomes slower. So, it goes down to 17 seconds, something like that. You can try up to 10 cores on the GPU nodes, right? if you compile it on the GPU nodes. You could compile that with OpenAP also on the Expanse CPU nodes, of course. And OpenACC, what we just added those pragmas, and oh my gosh, it's 500 seconds, right? It's super slow. So it's that's a complete fail, I would say, right? So what happened? Now you can set this environment where variable PGI ACC time equals 1 that activates profiling, and then you just run that executable again. And you will notice that here we have a compute region. A kernel is being launched 1,000 times. So because, you know, I set the maximum number of iterations to 1,000. And it takes about 1.5 seconds. So these are microseconds here, right? 1.45 million microseconds. But we have data copy in and data copy out, and they take like 22.5 seconds. It's like, okay, this is crazy. I'm copying data all the time, right? So all this time is spent transferring data between the host and the device. And basically what's happening in each iteration here in this while loop, you know, because I have this kernel here, OpenACC inspected this and says, okay, I need a new on the GPU and I need A on the GPU. So I copy these in from the CPU. I do my update and I copy those back, right? So you have these copies happen every iteration of the outer while loop. And of course, that's not necessary, but you know, OpenACC doesn't know that. I mean, there's no way for it to know, so you need to help the compiler. And that's where you need these data regions. So you add a pragma here, ACC data, copy A to the GPU and allocate a new on the GPU. And that's all we need in that region. And that will help the compiler because now once it generates this kernel, you know, A is already on the GPU. A new is already allocated in the GPU, so it doesn't need to copy the data, just keeps it on the GPU. And that pragma is outside of that while loop, so it will copy back only after the iterations are done, right? Of course, we want A back because we want to have the converged solution as an output. And with that, you have helped the compiler, and now you recompile it, and now we see if we run that on the GPU, those were the K80 Kepler architectures, so it's even 2 generations older than the V100s, is now 3.4 times faster than using 6 OpenAP threads, right? So now we got the time down from like 70 seconds to 5 seconds. And with that said, you know, OpenACC gives it much more options to control parallelization via their gang, worker, and vector clauses. And you know, that's the reason why I introduced you also to CUDA, because if you don't understand CUDA, you don't know what these things are, you know. So gangs correspond to blocks that share the resources, such as cache and so on. And the threads, they work in lockstep. So those are basically the warps, the vector clauses. And the worker are the threads per block. Right? So, and so by understanding more about the OpenACC execution model and the GPU hardware, you can get higher speed ups on even higher speed ups on the code. You know, there are further optimizations that you couldn't make. Often you have to reorganize the code. Often what you have to do is you have to rearrange how memory is laid out, how data is stored, and so on. And so it makes it easier than using CUDA, but depending on the problem and how your code looks like that you start with, it can still be a significant amount of work. There's some more information here about OpenACC and tips and tricks. This is for compilation. We've seen that there's not much I need to tell you. I just say we have a look at the hands-on exercises. Finally, these hands-on exercises, the GitHub repository README file has some information, right? For you to get started. There is this SIXPY example, and this Laplace 2D it contains this Jacobi iteration. Check the README files in those directories. I compile and run the OpenACC examples, and then you can so you can use the PGI compilers, or you can try to use NVHPC. So the NVIDIA compilers should be able to do this the same way. And then you can check the timings, you know, on the CPU and serial, OpenMP parallel, and running on the GPU with OpenACC, what you get on advanced GPU nodes and with the V100 GPUs. I have 2 or 3 more slides. I'll just briefly gloss over them. It's 3 slides. I just wanted to mention that these profiling tools, so the older tools, NVProf and NVVP, that's for CUDA, and the Nsight tools, really, those, you have the Nsight systems that gives you an overview of the entire code execution. This is really for graphics development. I have no clue about this, but Nsight Compute is detailed CUDA kernel performance. So once you get there, once you write CUDA code, these are very, very good tools, performance optimizations. And then there's also profiling tools for deep learning applications, so DLProf. And it works with NVTX plugins that are available in TensorFlow and PyTorch. And so there's already optimized versions by NVIDIA for their hardware that contain NVTX markers that basically tell the compiler, what's happening, and timestamps and so on, to annotate and focus on sections of code that are important to the user. And the DLProf itself calls these Nsight systems tools to collect profiling data and correlates it with a deep learning model. So if you have a deep learning application, you can also actually do some profiling. And you can get information about, are my GPUs being utilized, or do I do a lot of data transfers? Am I using the Tensor cores, yes or no? If not, what's the reason? Can I switch those on? How can I improve performance? So there's a lot of information like that. And that's really pretty straightforward to use. It just adds, for TensorFlow, no additional code modifications required. You just, if you want to profile a command line interface, just prepend it with DLProf, and then you can visualize the results with the DLProf viewer. So you'll get information like this. For PyTorch, you need to add a few lines of code to enable NVIDIA DLProf, PyTorch NVTX module, and other than that, it's the same. Then you can run DLProf on your code. And with that, thanks for listening. Let's go to the OpenACC tutorials. Just play around a little bit with that. And if you have any questions, I hope I can answer them. If you have any other problems, contact help@xc.org. And that brings me to the end of my slides. And here's information about the hands-on exercises for OpenACC.